I am Nagarna and my teammate is Nagasai from IIIitsricity. In this project, we are implementing real-time image processing on the Basys 3 FPGA development board using a grayscale image rendered through VGA and processed with the Sobel Edge Detection algorithm. Image processing is essential in fields like computer vision, robotics, and AI, where fast and efficient hardware-based edge detection can drastically improve system performance.
FPGA 128 into 128 grayscale image into a .cy file so by Python script, so it could be stored in the block RAM of the FPGA. So here I have uploaded image 50.cy from my laptop. So the width of the CY file is 8 bits and the depth of the CY file is 16,384 bits. This allows the image to be processed directly in hardware without relying on any external memory or processor. Then let's take a closer look at how this design works, starting from pixel reading, time control, and finally the real-time edge detection using the Sobel operator. This is the sample image we have used for this project. First we have converted this image into CY file using a Python script, and then we have used in this project. This is the Basys 3 board we have used for this project.
In this project, I am going to walk through the VGA Grayscale module. I wrote in Verilog for my FPGA-based image processing project. This module reads grayscale image data from VRAM and display it on a VGA monitor. First, we can see top module declaration. The module starts with basic inputs and outputs. We take a clock and reset as inputs, and we output horizontal and vertical sync signals along with 4-bit red, green and blue signals for VGA video. And then we use a simple clock divider to create a pixel clock from the system. This makes sure the image is synchronized correctly with the VGA display refresh rate. After that, we will initialize the VRAM interface. The grayscale image is pre-converted into a .coe file and loaded it into a VRAM. Here the VRAM is read only, and we pipeline the output using a register for timing stability. The VRAM stores 128x128 grayscale pixel values, so we use a 14-bit address line to cover the entire memory space. Then we will go with the VGA timing section. The core of the module is VGA signal generation using two counters, horizontal and vertical. We generate sync signals and identify the active video region. Horizontal timing resets every 800 cycles and vertical timing for every 524 seconds based on the resolution 640 480 at 6 edges VGA standard. Now we only show the image in a 128x128 pixel area on a VGA screen, specifically between pixel position 100 to 228 in both directions. In this region, we calculate the x and y coordinates and map them directly to the VRAM address. We fetch the grayscale value from VRAM and then apply a basic contrast enhancement using bit shifts, and then it sends to 3 color channels. This makes the image appear in grayscale on a VGA screen. This module forms the foundation for other effects like inversion or Sobel edge detection. It efficient, hardware friendly and runs in real time on an FPGA project.
This is the output you have got for grayscale image from I have uploaded a COE file. I have implemented color inversion on a grayscale image using Verilog and VGA output. The image is loaded from VRAM and displayed with its grayscale inverted in real time. So in first block, just like the grayscale module, we use a clock divider to derive the pixel clock from the system clock. The grayscale image is stored in VRAM as an 8-bit value per pixel, and we access it using a 14-bit address line, enough for our 128 into 128 resolution. So next is we follow standard 640 by 480 VGA timing using horizontal and vertical counters. Sync pulses are generated with appropriate delays, and we define a 128 into 128 active display window position from pixel 100 to 277 in both directions. Inside this window, X and Y coordinates and map them to a 1:1 DRAM address. Once we retrieve the grayscale value, we perform color inversion by subtracting it from 255 to 255 minus 255. 255 minus 255 gray, which flips dark areas to light and vice versa. To make the output smoother and visually appealing, we quantize the result to 32 level 2 using a bit shift operation and apply contrast enhancement using a lightweight arithmetic approach, basically gray by 8 plus gray by 16. We then clamp the value to a 4-bit range and send it to all 3 color channels, red, green and blue, to produce an inverted grayscale image on screen. This hardware accelerated approach ensures that inversion in display happens in real time, making it efficient and ideal for live video or embedded applications. This is the output you have got for color inversion image from grayscale image.
This Verilog module displays a 128 x 128 grayscale image from VRAM on a VGA monitor and adds a smooth RGB gradient colors based on the brightness levels. It shares by dividing the system clock by 4 to get a pixel clock, which drives both the VGA timing and VRAM reads. The image is stored in block RAM using an 8-bit grayscale format with addresses calculated from X and Y coordinates. VGA overview. Like standard VGA timing is used with horizontal and vertical counters generating H sync and Y sync signals. The actual image is displayed in centered 128 x 128 window from pixels 100 to 227 in both directions. Each visible pixel maps directly to one pixel in a VRAM. The grayscale value is quantized to 16 levels to reduce flicker and noise using bit shifts. Then, based on the quantized grayscale, we calculate the color gradients. Red increases when the brightness goes above 128. Green peaks near 128 for a balanced mid-tone. Blue fades as brightness increase. This creates a smooth RGB gradient effect that reflects the image brightness level. Finally, the outputs are clamped to a 4-bit range and sent to VGA using red, green and blue signals. This gives us a visually rich gradient display with real-time performance on FPGA hardware. By combining grayscale, quantization and dynamic RGB mapping, this module provides an efficient way to enhance grayscale images using color entirely in hardware.
This is the output you have got from RGB filter code. It performs real-time edge detection using the Sobel operator, displaying the result on a VGA monitor with 128 x 128 resolution. It begins by dividing the clock by 4 to generate a pixel clock. The image is stored in block RAM as an 8-bit grayscale file and read using calculated X and Y coordinates. The design follows standard 640 x 480 at 60 GHz VGA timing with sync signals and counters controlling the visible area. The image centered in a 128 x 128 region on the screen. To apply the Sobel filter, the module maintains 2 line buffers and a 3 x 3 sliding window of pixel data. These buffers let us efficiently access the neighboring pixels without needing the pause frame reads. It computes horizontal GX and vertical GY gradients using the classic Sobel kernel and approximates the gradient magnitude by adding their absolute values. A configurable threshold removes weak edges, only strong edges produce visible outputs. Scaled and clamped to 4-bit grayscale and then mapped to the red, green and blue VGA channels. The result is a sharp, real-time edge detected display rendered directly from memory using hardware logic, no CPU required. This approach is ideal for image processing on FPGA with minimum latency. This module demonstrates how simple logic, buffering, and classic operators like Sobel can perform real-time vision pipelines or embedded hardwares. And last, this is the Sobel Edge detected image. And thank you for watching this video.